Now there's a trick to finding spanning sets for a vector space. And the trick doesn't really have a name. So I want to do a couple of examples of it and see if you can catch on to what I'm doing. Let's let V be the space of polynomials of degree less than or equal to 3 with all coefficients of even powers of x equal and all coefficients of odd powers of x equal. Find a spanning set. So the trick is to put numbers into your typical element one at a time, and then every time you put a number in there, you think to yourself, what other numbers just got forced because of what I did? So these are polynomials of degree less than or equal to 3. So polynomials of degree less than or equal to 3 have the form a0 plus a1x plus a2x squared plus a3x cubed. But our condition says that the coefficients of even powers of x all have to be equal. And the coefficients of odd powers of x have to be equal. So let's put in constants one at a time. So let's pick the constant term. Well, let's say put in coefficients one at a time. So we'll start with the constant term. Let's say that one's b. Now the constant term is constant term times x to the 0th power, and 0 is even. So that means if we pick that one to be b, then we have to pick the coefficient of x squared to be b also. So choosing this coefficient actually chose two coefficients for us. And now let's look at the coefficient of x. Let's say that's going to be c. Now if the coefficients of all odd powers of x are equal, that means a c next to the x forces a c next to the x cubed. So then when you've put the coefficients in one at a time, obeying whatever conditions you have to obey, you take them out one at a time and say, well, b is multiplying, so this is b times 1 plus x squared, and then c is multiplying x plus x cubed. And then you think of your coefficients that you put in as linear combination coefficients now. So a spanning set is 1 plus x squared and x plus x cubed. Because every element of the space is multiple of 1 plus x squared plus multiple of x plus x cubed. These multiples disappear when you write the spanning set. It's what you're taking the multiples of that form the spanning set. So let's do another similar example. Let's let V be the 2 by 2 real matrices with A11 plus A22 equals 0. So the diagonal entries adding up to 0. Let's find a spanning set. So we write down a typical element. Putting in the coefficients one at a time and then thinking about what gets forced by each coefficient we put in. So a typical element is, let's say we put A in the 1, 1 position. Now we know that the 1, 1 entry plus the 2, 2 entry have to add up to be 0. So that forces the 2, 2 entry to be negative A, because otherwise they're not going to add up to 0. Alright, well so we've got 2 entries of this matrix now. Let's put another constant somewhere. Let's put a B in the 1, 2 position. Now the only condition we have is that the diagonal entries add up to 0. There's no condition on the 1, 2 coefficient. So by putting a B there, that doesn't force anything else to happen. Similarly, if we put a C here, there's no condition telling us what the 2, 1 position has to satisfy, how it has to relate to other entries. So putting a C here doesn't force anything else to happen in the matrix. So a typical element is this. It's going to be something in the form A, B, C, negative A, where A, B, and C are real numbers. Then we take those constants out and think of them as linear combination multiples. So this is A times what? It's A times the matrix 1, negative 1 on the diagonal, zeros elsewhere, plus B times the matrix 0, 1, 0, 0, plus C times the matrix 0, 0, 1, 0. So every element of this space has that form. And now that we've written it like this, it looks like multiple of this plus multiple of that plus multiple of the third thing. And a spanning set is what we're taking multiples of. It's 1, 0, 0, negative 1, 0, 1, 0, 0, 0, 0, 1, 0. The things that we're taking multiples of. Every element of the space can be written as a sum of multiples of these three things. That is, as a linear combination of these three things. All right, let's look at one more example. So let's consider the system of equations ax equals b, ax equals 0, which rho reduces to 1, negative 1, 2, 1, 0, 0, 0, 1, 2, 0. So whatever the original system was, this is what happens after row reduction, the row echelon form. Let's find a spanning set for the solution space. And we know that whenever we have a homogeneous system of equations, that is one that has 0 on the right-hand side, that the solutions to the system form a vector space. So let's find a spanning set. Well, we don't have any multiples in here, and we don't have any freedom to write different coefficients here. But let's start finding out what the space is. So we've got free variables x4 and x2, because the leading ones happen in columns 1 and 3. So the other variables are free. So let's let x4, which is a free variable, be s. And if that's s, then we can solve this equation. x3 plus 2s equals 0 implies that x3 equals negative 2s. Then free variable here, we'll let x2 be t. Then the first equation says that x1 minus t plus 2x3, 2 times negative 2s, plus x4, which is s, equals 0. And that means that x1 equals, we'll put a t on the other side, and then we've got minus 4s plus s. So this together is minus 3s. Put it on the other side, it becomes plus 3s. So x1, x2, x3, x4 equals, x1 is t plus 3s, x2 is t, x3 is negative 2s, and x4 is s. All right, and now we can see these two parameters, s and t, these two unknown constants. And those are what are going to help us find a spanning set. So we sort of look at them separately. How does t enter into this, and how does s enter into this? So this is t times 1, 1, 0, 0 plus s times 3, 0, negative 2, 1. And from this expression we can see that a spanning set for the solution space is the things that we're taking multiples of and adding together. We've got multiple of this plus multiple of that. So this and that form a spanning set. I can't find my the end sign, so the end.